The cosmos is vaster than we can possibly see, but what if everything we observe, from distant galaxies to the space around us, is only a fraction of the full picture? Our reality might be built upon hidden dimensions of existence, realms beyond the three spatial dimensions we move through. We are about to journey through 30 incredible theories that explore this mind-bending possibility. By the end, your entire perception of the universe will be fundamentally challenged. We will uncover where gravity might be hiding and how our entire cosmos could be a projection from a lower dimensional surface. What single idea would most shatter your understanding of reality? The first whispers of these hidden realms came not from science fiction, but from the quiet calculations of a mathematician nearly a century ago. In the 1920s, Theodore Kaluza presented a breathtakingly elegant idea. He suggested that the force of gravity, described by Einstein's general relativity, and the force of electromagnetism could be two sides of the same coin. The only catch, this beautiful unification required a fifth dimension, a direction in space we simply cannot perceive. Imagine a garden hose. From a great distance, it looks like a simple one-dimensional line. But if you were an ant crawling on its surface, you would discover a whole other dimension curled into a tiny circle, a world in itself. Kaluza and later Klein proposed that our entire universe might be like that. The three dimensions we know are vast and extended, while a fourth spatial dimension is curled up so small, perhaps 1 billion times smaller than an atom, that it remains completely invisible to us. Every point in our familiar three-dimensional space hides this unimaginably tiny coiled loop. This was not just a wild speculation. It was a precise mathematical framework that showed how the vibrations and geometry within this hidden fifth dimension could perfectly produce the electromagnetic force we observe. Kaluza-Klein theory was the grandfather of all modern multidimensional physics. It laid the foundational stone, proving that the laws of our universe might not make complete sense until we account for the secret, compact dimensions woven into the very fabric of reality. Kaluza's single hidden dimension was just the beginning. Decades later, physicists searching for a single theory to describe all of nature's forces stumbled upon a radical idea. What if the most fundamental pieces of the universe are not tiny dots, but unimaginably small, vibrating strings? This is superstring theory. These strings are so tiny that if an atom were the size of our solar system, a string would be no larger than a tree on Earth. Their vibration is everything. Just as a single violin string can produce different notes depending on how it is plucked, a single fundamental string can vibrate in a vast number of distinct patterns. One specific resonance might create an electron, another a quark, and yet another a particle of light. Every single thing we see, every force we feel, is just a different melody played on this cosmic symphony of strings. But for this beautiful mathematics to work, for the equations to balance and make sense, they demand something extraordinary. Our universe must have not 4, not 5, but 10 total dimensions. We experience only the 4 of space-time, leaving 6 spatial dimensions completely hidden from our view. Where could they possibly be? They are thought to be curled up into an intricate, complex shape at every single point in our familiar space, a shape known as a Calabi-Yau manifold. Picture the intricate, 6-dimensional geometry of one of these manifolds as the interior mechanism of a fine pocket watch. From the outside, you see only the smooth, simple face and hands. But inside, an entire universe of tiny, interlocking gears and springs performs a delicate dance, giving rise to the passage of time. In the same way, the specific, twisted geometry of these 6 hidden dimensions at every point determines the possible vibrational notes of the strings, which in turn dictates the very laws of physics in our visible universe. The mass of an electron, the strength of gravity, the existence of 3 families of particles, all of it could be a direct consequence of how these 6 secret dimensions are folded. This single theory elegantly suggests that the entire cosmic zoo of particles and forces emerges from the geometry of the unseen. Yet the story of strings did not end with 10 dimensions. The initial elegance of superstring theory soon revealed a strange fragmentation, giving rise not to one single theory but 5 competing versions. Each was mathematically sound, yet they seemed to describe different, contradictory sets of rules for the universe. It was as if 5 brilliant composers had each written a perfect symphony, but the melodies could not be played together. This deep puzzle remained until the 1990s, when a revolutionary idea emerged, uniting all 5 string theories under one grand, overarching framework. This is M-theory. Think of it as the master theory, the ultimate rulebook that shows how all 5 string theories are merely different viewpoints of a single, deeper truth. And this unification came with a stunning new requirement. M-theory demands an 11th dimension. This new dimension is not a tiny, curled-up loop like the 6 from before. It is fundamentally different, often visualized as a vast, expansive membrane, or brane for short. In this picture, our entire 4-dimensional universe, all of space and time, could be a 3-dimensional brane existing within a higher dimensional space. The implications of this single idea are staggering. M-theory is the strongest candidate we have for a true theory of everything. Its goal is to describe every single force and every single particle in one elegant, unified mathematical structure. It aims to show how the cosmic symphony of vibrating strings, playing out across 11 dimensions, gives rise to the 4 fundamental forces, the zoo of subatomic particles, and the very fabric of reality itself. All of existence, from the largest galaxy to the smallest quark, could be the result of geometry and vibration in a hidden, higher dimensional realm. This is the ultimate promise of M-theory, a single set of laws governing the cosmos in its entirety. But what if our universe is not the whole story? M-theory's 11th dimension opens the door to a truly radical possibility, the brane world scenario. This theory proposes that the universe we know and love, with all its galaxies, stars, and planets, is not a free-floating entity in a vast emptiness. Instead, it is a 3-dimensional membrane, or brane, suspended within a higher dimensional space called the bulk. Picture our entire cosmos as a single, impossibly thin slice of bread within an entire cosmic loaf. We are living our lives entirely within that slice. We can move left and right, forward and backward, up and down, but we are completely stuck within the confines of our own slice. The other slices in the loaf could be other universes with entirely different physical laws, forever separated from us by a gap we cannot cross. The forces and particles we are made of, like electrons and photons, might be like specks of poppy seeds or raisins embedded firmly in our slice. They are stuck to our brain, which is why we only perceive 3 spatial dimensions, but one fundamental force might be different, gravity. In this picture, gravity is not confined to our brain. It is the only force that can leak out, spilling into the higher dimensional bulk. This single idea offers a stunningly elegant solution to one of physics' greatest mysteries, why gravity is so unbelievably weak compared to the other fundamental forces. A simple magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. Why is gravity so feeble? The brane world provides an answer. The strength of a force diminishes as it spreads out through space. The electromagnetic force is concentrated on our 3-dimensional brane, so its strength is intense within our slice. But gravity, spreading out through all the higher dimensions of the bulk, becomes diluted. From our perspective, trapped inside the slice, it appears incredibly weak. We are only feeling a tiny fraction of its true strength, a faint echo of a force that is actually resonating throughout a much larger, hidden reality. This brane world concept leads us directly to a dramatic new theory of cosmic origins. Forget a single, explosive beginning. The Ekpyrotic universe theory proposes our universe was forged in a cataclysm of unimaginable scale, a collision between two of these cosmic branes. Picture two immense parallel sheets of reality drifting silently through the higher dimensional bulk. Over eons, they draw closer, pulled by an invisible force until they slam into one another. The impact would release an inconceivable amount of energy, flooding our brain with heat and matter, effectively igniting the hot, dense state we call the Big Bang. In this view, the Big Bang was not the absolute beginning of time and space, but a violent, transformative event within a much larger, pre-existing reality. What makes this idea even more profound is its cyclical nature. The theory suggests this collision was not a one-time accident. After the branes rebound from their impact, they drift apart, only to be drawn together once more, destined to collide again in a cycle that repeats for eternity. Each collision resets and reheats the universe, creating a new cosmic epoch from the ashes of the old one. This offers a breathtaking alternative to a singular creation event, an endless loop of universes being born, expanding, cooling, and then being reborn in another fiery collision. Our entire cosmic history, from the first flash of light to the formation of galaxies, could be just one chapter in an infinite story without a true beginning or end. But this idea of a universe projected from a boundary leads us to one of the most profound and counterintuitive theories in all of physics. The holographic principle proposes a staggering possibility. All the information that describes everything within a volume of space, every star, every planet, every person, could be entirely encoded on its lower dimensional boundary like a cosmic hologram. Think of the security hologram on a credit card. It appears as a full, three-dimensional object floating in space, yet all of its information is stored on the flat, two-dimensional surface of the plastic. The holographic principle applies this same logic to the universe itself. Our seemingly solid, four-dimensional reality of space and time might be nothing more than a magnificent projection from a vast, two-dimensional surface at the very edge of the cosmos. Every event that happens here in the volume of our world is just a translation of information stored on that distant, lower dimensional screen. This completely overturns our classical understanding of information and locality. We naturally assume that an object like a chair contains information within its own volume, in the precise arrangement of its atoms. But the holographic principle insists that the true description of that chair, its entire existence, is painted onto a faraway surface we can never see. It means that the universe we perceive, with its rich depth and texture, is fundamentally an illusion, a holographic movie playing out based on data stored on a simpler, lower-dimensional film. The very fabric of reality might be a kind of cosmic sleight of hand, where the true workings of the cosmos are written in a language of two dimensions, and we are simply living inside the projected image. The idea that extra dimensions could be curled up into a space smaller than an atom is mind-bending enough, but what if some of them are not tiny at all? What if they are large enough to be detected in a laboratory? This is the audacious proposal known as large extra dimensions. Theorists Nima Arkani-Hamed, Savas Dimopoulos, and Georgi Div-Ali turned the established view on its head. They suggested that the reason gravity is so weak compared to the other forces might not be an intrinsic property, but a simple matter of geometry. In their model, our entire universe of three spatial dimensions is still a brane, but it floats within a higher dimensional bulk that has extra dimensions far larger than anyone had previously considered. They could be as vast as a millimeter across, a cosmic-scale distance in the world of particle physics. In this framework, the particles of matter and the carriers of the electromagnetic, strong and weak forces are still stuck to our brane. They cannot leave, but gravity in the form of gravitons is different. It can travel freely through all the dimensions, including these large new ones. Think of our three-dimensional world as a vast flat plane. A force like electromagnetism is like sound traveling across this plane, its intensity concentrated and strong. But gravity is like a sound that can also travel upward into the open sky above the plane. Its energy spreads out into that immense volume, becoming fainter and more diluted for anyone listening down on the ground. This is the elegant solution to the hierarchy problem. The weakness of gravity is not a fundamental mystery. It is an illusion of our perspective. We are simply not feeling gravity's full strength because most of its influence is spilling out into dimensions that are, for now, just beyond our sight. The staggering implication is that gravity might not be weak at all. It might be just as potent as the other forces, but we are only experiencing a tiny, diluted fraction of its true power. Large extra dimensions offer one elegant answer, but another model presents an even more dramatic vision of the hidden cosmos. The Randall-Sundrum model introduces a universe where the fifth dimension is not just large, it is profoundly warped. Imagine our four-dimensional universe as one of two immense parallel walls facing each other across a chasm. This chasm is the fifth dimension, but it is not an empty, flat space. It is a highly curved, warped geometry known as an anti-de Sitter space. The warping is so extreme that the very scale of reality changes dramatically as you move across this hidden dimension. Picture a vast rubber sheet stretched tight, but with a powerful weight in the center creating a deep, funnel-shaped curve. Our brain, the wall we live on, sits on one far edge of this warp. The other wall, a second brain, exists on the opposite edge. Because of the intense curvature, the energy scale, the very intensity of physical laws, is exponentially different on each brain. On our brain, we experience the relatively low energies of the particles and forces that make up our world. But on the opposite brain, the fundamental energy scale could be trillions upon trillions of times higher, a realm of almost unimaginable power. This warping provides a breathtakingly simple resolution to the hierarchy problem, the puzzle of why gravity is so weak. The true, fundamental strength of gravity is set by the physics on that distant, high-energy brain. But by the time its influence travels across the warped geometry to reach our brain, its strength has been exponentially diluted. It is as if a powerful shout originates on one side of a wildly distorted canyon. The sound waves are stretched and weakened as they travel through the warped terrain, arriving at your ear as the faintest whisper. In this model, gravity is not inherently weak. We are simply living in the quiet, diluted zone of a cosmic landscape, far from the roaring source of its true power. The entire vast gulf between the strength of gravity and the other forces is not a fundamental mystery, but a natural consequence of the warped, hidden dimension that cradles our reality. The intricate shape of these 6 hidden dimensions is not just a random choice. It is governed by a very specific and beautiful class of geometric objects known as Calabi-Yau manifolds. These are the shapes into which the extra dimensions are curled, and their structure is everything. Imagine a form of impossible complexity, a multi-dimensional sculpture woven from space itself. It might have dozens or even hundreds of holes tunneling through it, like a hyperdimensional sponge or a cosmic version of an intricate sea creature's skeleton. The number and type of these holes, the twists and folds of the manifold, are not mere decoration. They are the cosmic dials that set the fundamental constants of our universe. The specific vibrational patterns that a superstring can produce are entirely dictated by the exact geometry of the Calabi-Yau manifold it is moving through. Think of the manifold as a kind of cosmic musical instrument. A violin's unique shape, the curve of its wood and the tension of its strings determines the exact notes it can play. In the very same way, the exact topology of a Calabi-Yau manifold determines the allowed vibrational notes for the superstrings. One specific resonance might correspond to an up quark. Another, with a slightly different frequency, might produce a down quark. The number of generations of particles, the masses of the electrons and neutrinos, even the very existence of the electromagnetic force, all of these seemingly arbitrary features of our reality could be direct mathematical consequences of the number of holes and the precise curvature of this hidden six-dimensional shape. This means that if you could somehow reach out and change the shape of the Calabi-Yau manifold at a single point in space, you would be rewriting the laws of physics for that location. You could make electrons heavier or light impossible to travel simply by altering the hidden geometry. In this breathtaking view, the universe is not governed by a list of arbitrary numbers in a physics textbook. It is governed by pure geometry. The reason we have the particles and forces we do is because the six secret dimensions of reality are curled up into one particular Calabi-Yau shape and not another. Our entire existence is a shadow cast by the intricate, invisible folds of space. This quantum strangeness forces us to ask what is really happening during a measurement. The many worlds interpretation offers a breathtaking answer, one that turns probability into a vast, branching reality. It suggests that every single time a quantum system faces a choice, the universe does not choose one outcome. Instead, it splits, with every possible outcome occurring in its own separate, fully realized branch of reality. Think of reality not as a single, flowing river, but as an endlessly dividing delta, with every trickle of water representing a complete and valid universe. In one branch, the radioactive atom decays and the Geiger counter clicks. In another, perfectly real branch born from the exact same moment, the atom does not decay and the counter remains silent. Both events happen with absolute certainty, but in worlds that are now forever separated, unable to communicate. These branching worlds are not hidden in some faraway dimension. They are right here, superimposed upon our own, but decohered, like radio stations broadcasting on frequencies we can no longer tune into. This interpretation frames every decision, every random quantum event as a point of dimensional splitting. A single moment of possibility does not collapse into one reality. It blossoms into a multitude of them. This means that for every choice you have ever made, there is a version of you living out the alternative in a parallel world. A universe where you took that different job, a world where a different sperm fertilized the egg, a reality where the dinosaurs were never wiped out by an asteroid. The totality of existence becomes a sprawling, ever-expanding tree of possibilities, where everything that can happen does happen somewhere in the multiverse. The reality we experience is just one leaf on an infinite tree, unaware of the countless other leaves rustling in a cosmic wind we cannot feel. The sheer number of possible Calabi-Yau shapes is not just large, it is cosmically incomprehensible. String theory allows for a landscape of possible vacuum states, a collection of stable configurations for the universe that could number 10 to the 500th power. That number is so vast it dwarfs the count of all the atoms in the observable universe. Each point in this landscape represents a unique universe with its own set of physical laws. The mass of the electron, the strength of gravity, the very number of dimensions that expand to vast sizes, all of these fundamental properties could be different. We are not talking about minor variations, but entire realities where nuclear forces are too weak to form atoms, or where gravity is so strong that stars collapse in moments. This is the string theory landscape, and it paints a picture of a multiverse of almost infinite variety. Within this endless cosmic array, the conditions for life as we know it are incredibly rare and specific. This leads directly to a profound and sometimes controversial idea known as the Holographic Principle. It suggests that we should not be surprised to find ourselves living in a universe with the right constants for life, because in a multiverse of all possibilities, we could only ever arise in one of the rare, hospitable corners. The laws of physics are not a unique, inevitable set of rules, but more like a winning lottery ticket drawn from a cosmic hat containing an almost infinite number of losing tickets. Our entire existence, then, becomes a selection effect. We are not observing a universe fine-tuned for life. We are simply life that has emerged within the narrow slice of the multiverse where such fine-tuning accidentally occurred. The landscape implies a staggering reality where every possible physical law is realized somewhere in a bubble universe forever beyond our reach. The relentless expansion of our universe seems to point toward a final, cold, and empty end. But what if that bleak future is not an end at all, but a transformation into a new beginning? Roger Penrose's conformal cyclic cosmology presents this exact vision. It proposes that our universe is just one chapter in an infinite series, each called an eon, where the ultimate fate of one cycle directly ignites the Big Bang of the next. This model hinges on a hidden dimension not of space but of scale. As a universe expands over trillions of years, all that remains are massless particles like photons drifting endlessly. In this state, the concept of scale becomes meaningless. A single wavelength of light is no different from the vast, empty expanse of the cosmos itself, because there is nothing left to measure it against. The universe becomes conformally invariant, a state where it has no defined size, only a shape. In this strange scalade state, the impossibly vast, cold, and empty future of one eon is physically identical to the hot, dense, and tiny singularity of a new Big Bang. The end seamlessly becomes the beginning. There is no violent collision of branes, no mysterious creation event. The transition is a smooth, geometric reset where the universe, having lost all sense of distance and time, is reborn. This cyclical process requires no new matter or energy continuing for eternity. The profound implication is that our universe had no true beginning and will have no final end. It is an endless loop of creation where the ghost of a previous eon might even leave faint imprints on the next, echoes of a cosmos that existed long before our own. While the universe appears smooth and continuous on our human scale, its most fundamental nature might be a seething, chaotic foam. Causal dynamical triangulations offers a radical way to picture this. This approach to quantum gravity does not start with strings or branes, but with the simplest possible building blocks, tiny geometric pieces of spacetime itself. Think of these as the universe's ultimate atoms of reality, not particles of matter, but irreducible fragments of dimension and causality. The theory builds the entire cosmos by connecting these elementary blocks together, following a simple set of rules to create a vast dynamic mosaic. Each block is a tiny, solid piece of geometry, a fundamental tile in the fabric of existence. As you combine more and more of them, a remarkable structure begins to emerge from the bottom up. The smooth, four-dimensional spacetime we know and love is not assumed from the start. Instead, it is the final product, a final, large-scale average of an almost unimaginable number of tiny, jittering pieces. On the very tiniest scales, at the Planck length, this model reveals a universe in a state of constant, violent fluctuation. The dimensionality of spacetime itself is not fixed. It writhes and changes. At one moment, a region might effectively have only two dimensions, like a flat sheet. In the next instant, it could become a wildly complex fractal structure with a fractional dimension, something more intricate than a surface but less filled in than a volume. This hidden, churning quantum geometry is the true foundation of reality. Our perception of a steady, reliable, four-dimensional continuum is an illusion of scale, much like the surface of a pond appears perfectly smooth and glassy from a distance. But up close, you see it is composed of countless frenetic water molecules, constantly jostling and rearranging. We are living on the calm, emergent surface of a quantum pond, entirely unaware of the frantic, dimensional dance happening just beneath our feet. While string theory weaves hidden dimensions into the fabric of reality, another grand vision approaches the puzzle from a completely different angle. Loop quantum gravity proposes that space itself is not a smooth, continuous backdrop. Instead, it is woven from a fabric of finite, indivisible threads. Picture the cosmos not as an empty stage, but as a dynamic tapestry made of a billion tiny, interwoven loops. These loops are the atoms of space, the smallest possible pieces of geometry. They connect with one another to form a vast, evolving web known as a spin network. Each intersection in this network, each node, represents a tiny grain of volume, while the links between them represent the areas that separate one grain from the next. This is the hidden architecture of the cosmos, a network of pure relationship and information that exists far below our ability to see. There are no extra, curled-up dimensions in this theory. The hidden dimensions here are the countless connections within the network itself, the intricate pathways of information that define how each grain of space relates to its neighbors. This spin network is not static. It evolves and changes in discrete steps like the ticking of a cosmic clock. Each tick represents a fundamental unit of time, a single quantum of temporal change. In this dance, the network reorganizes itself, with loops merging and splitting, creating a dynamic, pulsating geometry that we perceive as the smooth, flowing spacetime of general relativity. The three-dimensional space we move through and the time we experience are merely the large-scale, calm average of this frantic, quantum geometric dance. This leads to a stunning prediction. Spacetime is not infinitely divisible. If you could peer down to the Planck scale, a distance of 10 to the negative 35 meters, you would see reality pixelate. You would witness the granular, atom-like structure of the universe, a foaming sea of geometric quanta. This fundamental graininess prevents the singularities that haunt classical physics, like the infinite density at the heart of a black hole. There is no true infinity because space itself cannot be compressed beyond its smallest, fundamental building blocks. In this view, the hidden dimensions are not directions you can move in, but the very connectivity that allows space to exist at all. This radical shift in perspective asks if space-time is even a fundamental ingredient of reality. Perhaps the four dimensions we inhabit are not the foundation of the universe, but a secondary effect, a collective hallucination born from something far more basic. The theory of emergent spacetime proposes exactly this. We are familiar with emergent properties in everyday life. Think of the temperature of a gas. The gas itself has no single temperature. That concept of warmth is not a fundamental property of any one atom. Instead, it emerges from the collective, frenetic motion of trillions upon trillions of molecules. The smooth, continuous experience of temperature is a large-scale illusion created by an underlying sea of discrete, jittering parts. In the very same way, the smooth, continuous fabric of space-time and the force of gravity may not be fundamental. They could be emergent phenomena arising from the collective behavior of an unimaginably vast number of quantum components. What is the quantum motion that gives rise to the geometry of the cosmos? The leading candidate is quantum entanglement. This is the mysterious connection that can link two particles across any distance, instantly correlating their fates. Now imagine not just two particles, but a near-infinite network of them, all entangled with each other in an impossibly complex web. Each quantum connection, each thread of entanglement, acts like a single stitch in the fabric of reality. Where the entanglement is dense and strong, space is highly connected, allowing for a smooth, continuous geometry. Where there is little or no entanglement, space effectively falls apart, becoming disconnected and unstructured. The force of gravity itself might be a direct consequence of this underlying quantum architecture. Just as a change in the average motion of molecules alters the temperature, a change in the pattern of entanglement could alter the curvature of spacetime, creating what we perceive as the gravitational force. An object with mass might be understood as something that disrupts or reorganizes the local entanglement network, and the resulting reshuffling of quantum connections propagates outward as the warping of space we call gravity. This suggests a breathtaking conclusion. The hidden dimensions of our universe are not extra, curled-up directions. They are the countless pathways of quantum information flowing through an entangled network. The three dimensions of space and the flow of time are simply the most efficient way this cosmic web organizes its immense number of quantum connections. We are not living in a container of pre-existing space-time. We are living inside a magnificent, dynamic tapestry woven entirely from quantum relationships, and the dimensions we move through are the pattern that tapestry creates. All of this quantum architecture leads to a terrifying puzzle at the edge of a black hole. The very nature of reality seems to break down, forcing physicists to confront a paradox so profound it threatens our understanding of information itself. This is the black hole information paradox. According to Einstein's general relativity, if you were to fall into a black hole, you would cross the event horizon without noticing anything special, at least at first. It is a point of no return, but not a physical barrier. Yet quantum mechanics insists that information can never be truly destroyed. Every bit of data about what you are made of, every particle, every quantum state, must be preserved in some form. The paradox emerges from Stephen Hawking's discovery that black holes are not entirely black. They slowly evaporate, radiating away their mass over eons until they potentially vanish completely. If the black hole disappears, what happens to all the information about everything that ever fell in? Is it irretrievably lost, violating a fundamental law of quantum physics? Or is it somehow encoded in the Hawking radiation, a scrambled, nonsensical code that seems impossible to decode? This contradiction between the smooth spacetime of relativity and the ironclad rules of quantum mechanics creates a crisis at the horizon. One proposed resolution is as violent as it is controversial: the firewall. To preserve the laws of quantum mechanics, the event horizon might not be a peaceful place at all. Instead, it could be a searing wall of unimaginably high energy particles, a literal firewall that would instantly incinerate anything crossing it. This solves the information problem by ensuring the information never actually enters the black hole, but is instead smeared and encoded on the fiery surface. Yet this creates its own terrible problem, violating Einstein's principle that falling through the horizon should be an unremarkable event. We are left with a brutal choice: either the smooth spacetime of general relativity is wrong, or the sacred principle of quantum information conservation is wrong. Perhaps the answer lies in the holographic principle we encountered earlier. The information is not lost inside the black hole because it was never truly inside to begin with. Just as a hologram projects a three-dimensional image from a two-dimensional surface, all the information about what falls into a black hole might be entirely encoded on its two-dimensional event horizon. The interior we imagine, with its crushing singularity, could be a projection, an illusion created by the data painted on the surface. When the black hole evaporates, this information is not destroyed, but slowly and chaotically released back into the universe through Hawking radiation. Another, even more mind-bending possibility is that the information does not come back out into our universe at all. The intense gravitational collapse of a black hole might warp the fabric of reality so severely that it pinches off, creating a new, disconnected spacetime, a baby universe. All the information that fell into the parent black hole is not destroyed, but simply transferred into this new cosmic realm, a universe born in the heart of darkness, forever separated from our own. This means black holes could be cosmic nurseries, each one a gateway to a new reality with its own laws and dimensions, a hidden dimension of existence not of space, but of entire cosmic lineages branching off from our own. This strange link between quantum information and spacetime geometry leads us to an even more profound connection. The AR equals EPR conjecture proposes a breathtaking unity between two of Einstein's most famous ideas he always believed were entirely separate. On one side, we have ER, the Einstein-Rosen bridge, which is the formal name for a wormhole. This is a tunnel through the fabric of space-time, a shortcut connecting two distant points in the universe. On the other side, we have EPR, named for Einstein, Podolsky, and Rosen, the paper that first identified the spooky phenomenon of quantum entanglement. For decades, these two concepts lived in different worlds. Wormholes were a wild prediction of general relativity, while entanglement was the bizarre heart of quantum mechanics. This new conjecture boldly states they are one and the same thing. It suggests that any two particles that are quantum entangled are not just mysteriously linked in a statistical sense. They are literally connected by a microscopic wormhole, a tiny bridge woven through the hidden architecture of spacetime. Imagine two electrons born together, forever linked no matter how far apart they fly. We usually think of their connection as a ghostly, non-physical link, a piece of shared information. But AR equals EPR paints a radically different picture. It says that a physical, geometric bridge exists between them, a tunnel so incredibly tiny and unstable that it remains completely invisible and untraversable. This wormhole is the physical manifestation of their quantum bond. The spooky action at a distance that so troubled Einstein is not action through space, but action facilitated by a secret shortcut through space. This single idea has staggering implications for the fabric of reality. It hints that the weirdness of quantum mechanics and the smooth geometry of general relativity are not two separate theories in conflict. They are two different descriptions of the same underlying reality. Quantum entanglement, the most non-classical phenomenon, might be the very thread that stitches the classical fabric of spacetime together. Every quantum connection could be a tiny stitch in the cosmic tapestry, and the sum total of all these entangled stitches is what we experience as the smooth, continuous dimensions of our universe. The hidden dimension here is not an extra direction to move in, but the vast network of microscopic wormholes that undergird everything, connecting every entangled particle in a web of geometric unity. This startling conclusion forces us to confront a deep philosophical question about our own place in the cosmos. Why does our universe seem so perfectly tailored for life? The constants of nature appear finely tuned. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. If the nuclear forces were any weaker, hydrogen would never fuse into helium and stars would never ignite. The cosmic ledger is balanced on a razor's edge. One compelling answer emerges directly from the hidden dimensions we have been exploring. The vast landscape of possible Calabi-Yau shapes, each defining a different set of physical laws, provides a physical mechanism for this apparent fine-tuning. We call this the Anthropic Principle. It is not a theory of physics itself, but a statement about selection. In a multiverse containing every possible universe, from the utterly barren to the wildly unstable, conscious observers can only emerge in the rare pockets where the numbers just happen to be right. We are not seeing a universe designed for us. We are simply the life forms that must, by logical necessity, find ourselves in a universe capable of producing us. Think of it as a cosmic lottery with an almost infinite number of tickets. The overwhelming majority of those tickets are losers, representing universes where atoms cannot form, or where time ends instantly, or where the very concept of structure is impossible. Our universe is one of the incredibly rare winning tickets, a cosmos where the hidden dimensions curled up in just the right way to allow for galaxies, planets, and ultimately, beings who can look up and wonder why. The profound and somewhat humbling implication is that the fundamental laws we work so hard to uncover may not be fundamental or inevitable at all. They could be purely local bylaws, the accidental outcome of a random geometric roll of the dice in a higher dimensional reality. Our entire existence becomes a magnificent cosmic coincidence. Our search for hidden dimensions is not confined to blackboards and equations. It is happening right now, deep underground on the border of France and Switzerland, inside the most complex machine ever built. The Large Hadron Collider smashes protons together at nearly the speed of light, recreating conditions a fraction of a second after the Big Bang. Within the debris of these unimaginably violent collisions, physicists are hunting for the fingerprints of extra dimensions. One of the most dramatic signatures would be the sudden creation of a microscopic black hole. If our universe has large extra dimensions, the true scale of gravity could be much higher, making it possible to concentrate enough energy in one spot to warp space into a tiny, transient black hole. It would not devour the Earth. Instead, according to Hawking's theory, it would instantly evaporate in a flash of radiation and particles, leaving a very specific and explosive pattern in the detectors. Scientists have scoured the data for this telltale burst, but so far the silence has been deafening. Another key signature involves the missing gravity. If gravitons, the hypothetical carriers of gravity, can indeed leak into the bulk, then sometimes in a high-energy collision, a graviton could simply vanish, carrying its energy away into a hidden dimension. From our perspective on the brane, this would look like a dramatic event where momentum and energy suddenly and inexplicably disappear from the collision. Detectors like ATLAS and CMS are exquisitely tuned to spot this imbalance, searching for events where the books of cosmic energy simply do not add up. A third clue could come from strange new particles, heavier copies of known particles that appear as brief resonances. These could be explained by particles that, in a higher dimensional space, have vibrational modes along the extra compact directions. The lack of any such discoveries so far is not a failure. It is a powerful form of guidance. Each non-discovery tells us that if extra dimensions do exist, they are either smaller or more warped than our current energy levels can probe. The empty silence from the LHC is slowly mapping the boundaries of possibility, telling us where the hidden realms cannot be, and forcing theorists to refine their most ambitious dreams of a multidimensional cosmos. The sheer weakness of gravity is a ghost haunting modern physics. Why should one force be so unimaginably feebler than all the others? This is the hierarchy problem, a puzzle that seems to demand an answer beyond our four-dimensional view. Yet the very theories of hidden dimensions offer not one, but several breathtakingly elegant solutions, each reshaping our understanding of this fundamental imbalance. Large extra dimensions resolve it through simple dilution. In this picture, gravity is not inherently weak. Its force merely spreads out, spilling into dimensions far larger than an atom, losing its intensity before it can be felt on our three-dimensional brane. The force we experience is a faint shadow of its true strength. The Randall-Sundrum model with its warped geometry offers an even more dramatic mechanism. Here, the weakness is not dilution, but a cosmic redshift of force. The true, raw power of gravity is anchored on a distant brane, a high-energy wall separated from us by a deeply curved fifth dimension. By the time gravity's influence travels across this warped landscape to reach our world, its strength has been exponentially suppressed, arriving as the faint whisper we measure. And the original brane world scenario frames it as a matter of confinement. The particles that make up our bodies and our world are stuck to our brane, their forces concentrated and potent within our slice of reality. Gravity alone is free to roam the bulk, its influence bleeding into the wider, higher-dimensional cosmos. We are like flatlanders living on a vast sheet, only feeling the tiny fraction of a force that operates in a much grander theater. Three different theories, each employing a unique property of hidden dimensions, all converging on a single, profound insight. The hierarchy problem may not be a problem at all, but the most compelling clue we have that our universe is part of a far richer, multidimensional reality. This single number, the cosmological constant, represents the energy of empty space itself. It is the engine of cosmic acceleration, a faint pressure woven into the very fabric of the void. Yet calculating its value has produced what many call the worst theoretical prediction in the history of physics. When we apply our best theories of quantum fields to the vacuum, we find that empty space should be seething with a tremendous energy, a violent froth of virtual particles popping in and out of existence. This quantum jitter should give the vacuum an energy density so immense that it would have ripped our universe apart in the first instant of the Big Bang. The math predicts a number like 1 followed by 120 zeros, but our actual observations of the cosmos tell a completely different story. The measured value of dark energy is incredibly small, a 1 with only 122 zeros after the decimal point. The difference between these two numbers is greater than the difference between the size of a single proton and the entire observable universe. It is an error so colossal, so embarrassing, that it points to a fundamental gap in our understanding of reality. How can the vacuum be so energetic in theory, yet so quiet in practice? The answer might be hidden within the dimensions we cannot see. The string theory landscape offers a possible escape from this crisis. Remember the vast number of possible Calabi-Yau shapes, each one defining a different universe with different physical laws and a different value for the vacuum energy. In this cosmic lottery, the vast majority of universes have a huge positive cosmological constant, blowing themselves to pieces instantly. Another vast majority have a large negative value, causing an immediate gravitational collapse. But scattered like rare jewels across this landscape are a tiny, tiny fraction of universes where all the competing contributions to the vacuum energy, the positive and the negative, almost perfectly cancel out. They don't cancel to exactly zero, but to a tiny leftover residue. Our universe, by sheer chance, must be one of these rare survivors. The cosmological constant is not fine-tuned by any grand design. We simply find ourselves in one of the few cosmic neighborhoods where the vacuum energy is small enough to allow for the formation of galaxies, stars, and planets. The Holographic Principle provides the selection effect. We could not exist in a universe where the calculation worked perfectly, because such a universe would be empty and lifeless. The very fact that we are here to be baffled by the smallness of dark energy is a powerful clue that we live in a special place within a much larger multiverse. The cosmological constant problem transforms from a mathematical failure into a signature of our address in the hidden dimensional landscape, a quiet reminder that our entire reality rests upon a delicate and improbable cancellation written into the geometry of the unseen. Hidden within the mathematical heart of supersymmetry lies a profound connection to the very dimensions we cannot see. This elegant theory proposes a deep, fundamental symmetry between the two great families of particles that make up our universe. On one side are the fermions, the solid building blocks of matter, like electrons and quarks. On the other are the bosons, the forceful messengers that carry the fundamental interactions, like photons and gluons. Supersymmetry suggests that for every known fermion, there must be a corresponding bosonic superpartner, and for every known boson, a fermionic twin. The electron, a fermion, would be paired with a boson called the selectron. The photon, a boson, would be paired with a fermion called the photino. This beautiful pairing does more than just double the number of elementary particles. It tames the violent quantum fluctuations that would otherwise rip spacetime apart, offering solutions to some of physics' most stubborn problems, like the hierarchy of forces. But this mathematical elegance comes with a hidden requirement: for supersymmetry to be woven into the fabric of gravity itself, creating a theory known as supergravity. The equations demand a stage with more room to operate. They inherently require extra spatial dimensions. The intricate dance between a particle and its superpartner cannot be fully described in just the 4 dimensions we experience. The symmetry only finds its full, consistent expression when it is allowed to vibrate through a reality with more degrees of freedom. This is why supersymmetry is such a central pillar of superstring theory and M-theory. The theory's very consistency is married to the existence of these hidden realms. If these superpartners are real, they are immensely heavy, which is why our current colliders have not yet created them. They existed in great numbers in the high-energy frenzy of the early universe, but as the cosmos cooled and expanded, they decayed away, leaving behind the asymmetric world we see today. Finding one of these particles would be a monumental discovery, but its implications would reach even further. The specific properties of a superpartner, its mass and how it interacts, would be a direct reflection of the geometry of the compactified dimensions. Detecting a selectron or a photino would be like finding a key. That key would not only unlock a new chapter in particle physics, but would also begin to reveal the precise shape of the hidden, six-dimensional Calabi-Yau manifold that dictates the laws of our reality. The hunt for these shadow particles is in essence a hunt for the architectural blueprints of the cosmos. But these cosmic membranes are not just featureless walls. A specific and powerful kind of brane, known as a D-brane, acts like an anchor point for the universe's most fundamental threads. In string theory, strings can be either closed, forming tiny loops, or open with two distinct ends. A D-brane is a dynamic, multidimensional object where the endpoints of these open strings are firmly attached. Think of a D-brane as a vast, flexible canvas. The open strings are like intricate brushstrokes pinned to this canvas, and their vibrations paint the physical phenomena we observe. A string vibrating in one specific pattern while attached to a D-brane might manifest as a particle of matter. A string vibrating in a different pattern could create a force carrier like a photon. The very existence of the forces that govern our world, the so-called gauge forces, emerges directly from the interaction of open strings with these D-branes. Their dimensionality is also crucial. A D0 brane is a single point, a D1 brane is a string-like filament, a D2 brane is a membrane, and so on, all the way up to higher dimensional structures. Our entire universe could be a vast D3 brane, with all the particles and forces we know consisting of open strings stuck to its surface. This makes D-branes indispensable tools because they allow physicists to explore the non-perturbative regime of string theory, the realm of strong interactions where previous mathematical approximations failed. Their power became stunningly clear when they were used to count the quantum states of certain black holes. By configuring a collection of D-branes in just the right way, scientists could calculate the entropy of a black hole, matching the famous result predicted by Stephen Hawking. This was a monumental achievement. It suggested that a black hole's mysterious, hidden information could be understood as the specific vibrational states of strings attached to D-branes residing at its horizon. These are not just abstract mathematical curiosities. They are the dynamic stages upon which the drama of our cosmos plays out, providing a tangible, physical framework for understanding everything from the forces that bind atoms to the darkest secrets of spacetime itself. The elegance of the string theory landscape, with its near-infinite possible universes, might feel like the ultimate freedom for physics, but a powerful new set of ideas argues the opposite. There is a fence around this landscape, separating the truly possible worlds from those that are mathematically alluring but physically forbidden. Welcome to the swampland. This concept draws a sharp line between the consistent theories of quantum gravity that could describe a real universe, the landscape, and those that are mathematically possible yet ultimately inconsistent, the swampland. They are trapped, unable to connect to a full theory of quantum gravity, and thus represent dead ends for reality. One of the most compelling entries in this rulebook is the distance conjecture. It states that as you move an infinite distance in the theoretical space of field configurations, an infinite tower of new particles must appear, becoming exponentially lighter. To grasp this, picture a lone explorer on an endless, featureless plain. With every step they take away from their starting point, the air seems to fill with an ever-growing cloud of dust motes, each one a new, nearly massless particle. The further they go, the more motes appear until they are wading through a thick fog of new physics. This is not just abstract math. These infinite distances in field space are deeply connected to the geometry of the extra dimensions. Moving that far theoretically corresponds to making a dimension grow infinitely large, or alternatively, to making it shrink to an infinitely small point. The conjecture tells us that our universe cannot actually do that. Before you reach that true infinity, the very framework of effective field theory that we use to describe physics breaks down, overwhelmed by the swarm of new light states. This single idea places incredibly strict constraints on what is physically possible. For instance, it suggests that the vacuum energy, our cosmological constant, cannot be a fixed positive number across all of space and time. True, stable dark energy might be impossible, hinting that our current accelerating expansion is a temporary phase, or that we live in a very special metastable pocket. The swampland criteria act as a cosmic editor, ruthlessly cutting theories that, while mathematically beautiful, could never actually breathe life into a real cosmos. They tell us that the hidden dimensions are not a playground for any arbitrary geometry, but a tightly regulated foundation, bound by rules that ensure the universe they build is coherent, dynamic, and ultimately real. The birth of our universe in a burst of inflationary expansion solved many cosmic puzzles, but it also created a profound mystery of its own. To produce the gentle seeds for all future galaxies, inflation had to stretch minuscule quantum fluctuations in the fabric of spacetime to astronomical sizes. Yet this process implies that every structure we see today, every galaxy and cluster, originated from a fluctuation with a wavelength far, far smaller than the Planck length, the scale where spacetime itself is thought to lose all classical meaning. This is the trans-Planckian problem. How can we trust a theory that relies on physics from a regime where our very concepts of space and time are expected to break down completely? It is like tracing the origin of a mighty river to a single water molecule that should not even exist. The problem suggests that our standard picture of inflation is incomplete, missing a crucial piece of new physics that governs the deepest, most fundamental level of reality. This is where the hidden dimensions we have explored could provide the critical missing link. If spacetime is not a smooth continuum, but has a discrete, granular structure at the Planck scale, as suggested by loop quantum gravity or causal dynamical triangulations, then there is a fundamental cutoff. Fluctuations cannot be squeezed to arbitrarily small sizes. They would bounce or reflect off this fundamental graininess, altering their initial conditions before being stretched by inflation. The specific nature of this granularity, potentially shaped by the geometry of compactified dimensions, would then be imprinted onto the pattern of the cosmic microwave background, the afterglow of the Big Bang. The subtle variations in this ancient light could be carrying a faint echo of the universe's true, multidimensional architecture. Hidden dimensions might not just be a feature of our cosmos. They could be the very reason our cosmos has the structure it does, providing the necessary physics to make sense of our own dramatic beginning. Our reality might be a cosmic shield against its own dissolution. Deep within the holographic principle lies a theory so abstract and powerful it redefines the nature of existence itself. It proposes that space-time and its geometry are not fundamental, but emerge from a quantum error-correcting code. In our digital world, error-correcting codes protect information. When you send a message, extra bits of data are added so that if noise corrupts part of the signal, the original information can still be perfectly reconstructed. The universe, this theory suggests, operates on the same principle, but using the strange laws of quantum mechanics. The fundamental ingredients of reality are not particles or forces, but quantum bits or qubits, storing information in a vast, entangled network. This raw quantum information is incredibly fragile. A single local disturbance, a tiny bit of decoherence, could scramble it into nonsense, making a stable, classical world impossible. So how does our robust, predictable universe emerge from this fragile quantum soup? The answer is in the way the information is stored. The code is designed so that any piece of logical information, like the existence of a particle at a point in space, is not stored in one single location. Instead, it is spread out or delocalized across a vast web of entangled qubits on the lower dimensional boundary. To destroy that one piece of information, you would have to destroy a significant fraction of the entire system all at once. A local error, a tiny scratch on the cosmic hard drive, cannot damage the true logical data. It only affects the redundant physical bits. The system automatically corrects for it, leaving the encoded information intact. This is where space-time itself comes from. The perception of a local, three-dimensional world where objects are separated by empty space and interact in predictable ways is the result of this incredibly efficient, fault-tolerant storage system. The distance between 2 points in space is not a fundamental property. It is a measure of how difficult it is for an error to corrupt the quantum information that describes those 2 points. If their information is stored in highly entangled qubits, they are effectively close together and errors can be easily corrected. If their information is stored in largely separate sets of qubits, they are far apart and correlated errors between them are unlikely. In this breathtaking view, the solidity of the chair you are sitting on and the vast emptiness between stars are not primary features of reality. They are the ultimate illusion, a protected, classical projection of quantum data that has been cleverly distributed to withstand the chaos of its underlying nature. The hidden dimension here is not a direction, but the sheer redundancy of the cosmic code, a design so brilliant that it conjures an entire universe from the brink of its own perpetual noise. Gravity's ghostly weakness hints at dimensions hidden on a microscopic scale. But what if the truth is far stranger? Could some of these extra dimensions be not tiny, but vast, macroscopic realms existing alongside our own? This is perhaps the most science fiction-like possibility of all, the idea that hidden worlds could be just a millimeter away, separated by a direction in space we simply cannot point toward. For such a dimension to affect all forces equally, it would have to be infinite and flat, a possibility our most precise experiments have already ruled out. We would see bizarre quantum effects and deviations in the inverse square law of gravity at measurable distances, effects that have never appeared. The universe, it seems, is not built that way. Yet the door is not completely closed. A more exotic, speculative idea allows for a different kind of macroscopic dimension. Imagine a shadow brane, a parallel universe that runs alongside our own, separated by a macroscopic gap in a higher dimensional bulk. The crucial difference is that this shadow brane interacts with our own only through the faintest of whispers, perhaps solely via gravity. The other fundamental forces, the glue that binds our atoms and allows us to see light, are completely confined to our own cosmic slice. This means an entire universe with its own stars, planets, and perhaps even life could be floating right beside us, forever invisible and untouchable. We would have no way to see its light, no way to touch its matter. The only sign of its existence might be a faint, unexplained gravitational tug, a ghostly presence from a world that is, for all other purposes, completely isolated. These parallel worlds would be true neighbors in a higher dimensional space, yet separated by a chasm of physical law, hiding in plain sight just beyond the reach of every sense but the most subtle and mysterious force in the cosmos. Throughout this exploration, a single, powerful current has been flowing just beneath the surface of every theory. It is the deep-seated belief that at its heart, the universe is not a collection of messy, contradictory rules, but a unified whole, structured by an inherent and breathtaking mathematical beauty. The drive to discover hidden dimensions is not about inventing complexity. It is a necessary step in the quest for ultimate simplicity. For nearly a century, physics has been fractured by a fundamental schism. On one hand, we have Einstein's general relativity, a masterpiece of geometry that paints gravity as the elegant curvature of a smooth, continuous spacetime. It describes the cosmic dance of planets and galaxies with stunning precision. On the other hand, we have quantum field theory, the rulebook for the subatomic world, a realm of frantic probability, discrete particles, and fundamental uncertainty. This theory governs the other three forces with immense success. The problem is that these two pillars of modern physics are fundamentally, violently incompatible. When their equations are forced to meet, they produce nonsensical answers, infinities that shatter the framework of prediction. It is as if one brilliant composer wrote a symphony for a vast, serene orchestra, while another wrote a frenetic, powerful piece for a jazz quartet. Both are beautiful on their own, but when played together in the same hall, they create nothing but cacophony. The introduction of extra dimensions is the conductor's score that finally allows both symphonies to be heard as one. It is not a random addition. The mathematics itself demands it. When physicists sought a single, coherent framework to describe all of nature's forces, they found that the equations only balanced, the infinities only vanished when the stage of reality was given more room. The vibrational patterns of strings required more dimensions to produce the full spectrum of particles and forces. The unification of gravity with the other forces in theories like Kaluza-Klein and later M-theory was not possible in a mere 4 dimensions. The math simply would not work. This is a crucial point. The extra dimensions are not a convenient excuse for things we do not understand. They are the inevitable, natural consequence of the search for a single, elegant set of laws. The universe's hidden architecture appears to be inherently and beautifully multidimensional. What we perceive as the complex zoo of particles and forces in our 4-dimensional experience might just be the shadow of a far simpler, more symmetrical reality existing in a higher dimensional space. The messiness we see could be a projection, a broken symmetry, while the true, core description of existence is one of profound and unified elegance. This pursuit of mathematical beauty is more than just an aesthetic preference. Time and again in the history of science, the most beautiful and elegant mathematical solution has turned out to be the one that describes nature most accurately. From the simple inverse square law of gravity to the complex symmetries of the Standard Model, beauty has been a reliable guide to truth. The drive to unify relativity and quantum mechanics through hidden dimensions is the ultimate expression of this principle. It is the faith that the cosmos is not a tangled knot of arbitrary rules, but a masterpiece of minimalist design, whose deepest secrets are written in a language of geometry and dimension that we are only just beginning to decipher. These mathematical revelations force us into a profound and unsettling territory, the nature of reality itself. If the cosmos is fundamentally built upon hidden dimensions, then our entire experience of the world is a magnificent shadow play. We are confined to a narrow slice of a much grander existence, forever unable to perceive the full stage. This directly challenges our most basic assumption that what we can see and touch is the entirety of what is real. Consider a simple object like a book. To us, it is a solid, 3-dimensional thing with a fixed location. But if our 3-dimensional space is merely a brane within a higher dimensional bulk, that book is not just here. It extends into a direction we cannot point to, a dimension we cannot move along. Its true, complete form is something we can never experience. This shatters the classical idea of locality, the principle that objects can only be influenced by their immediate surroundings. In a universe with extra dimensions, 2 points that seem astronomically far apart in our 3-dimensional space could be mere millimeters away from each other through a shortcut in the bulk. The very meaning of here and there becomes fluid and ambiguous. Where, then, is the book truly located? Its location is not a simple address in our familiar space, but a coordinate in a cosmos with more directions than we can comprehend. This line of thinking resonates with ancient philosophical ideas that have persisted for millennia. The concept of higher planes of existence, of realms beyond the physical senses, is a cornerstone of many spiritual traditions. Plato's theory of forms suggested that our tangible world is a flawed reflection of a more perfect, ideal realm. The multidimensional cosmos suggested by modern physics offers a startlingly similar framework, though grounded in mathematics rather than metaphysics. Our universe, with its specific laws and particles, could be just one particular configuration, one specific form, instantiated on our brane. The true, fundamental reality might be the higher dimensional bulk, a realm of pure geometry and vibration from which our world projects. This forces a difficult question. If a dimension exists but we, by our very biological and physical nature, are forever barred from perceiving it, can we say it is real? Our definition of reality is tied inextricably to our senses and our instruments, which are all built to operate within the 4 dimensions of space-time. Something that does not interact with our light, our matter, or our forces in any way other than the faint, ghostly tug of gravity might as well not exist for all practical purposes. And yet, the mathematics insists it is there, shaping everything we are and see. The strength of gravity, the existence of matter, the very laws of physics, all seem to depend on the architecture of these unseen realms. So which is more real, the world we experience or the hidden dimensions that dictate its rules? We are left with a humbling conclusion. We may not be the central observers of a universe designed for our perception. We are more like prisoners in a cave, watching shadows dance on a wall and mistaking them for the whole of existence, while the true, vibrant, and multidimensional reality unfolds in a light we cannot see. Our search for the universe's hidden architecture is far from over. The next generation of experiments stands poised to transform these mathematical dreams into tangible facts. Imagine a particle collider of unprecedented scale, a machine that dwarfs even the Large Hadron Collider. Future colliders could reach energies high enough to finally create microscopic black holes, the definitive signature of large extra dimensions, or to produce the elusive superparticles predicted by supersymmetry. Each new energy frontier is a deeper probe into the quantum foam, potentially revealing the granular structure of space-time or the vibrational notes of strings. In space, the Laser Interferometer Space Antenna, LISA, will open a new window on the cosmos. This trio of satellites will detect gravitational waves from the mergers of supermassive black holes and from the earliest moments of the universe. These ripples in spacetime are a pristine messenger. If gravity is indeed leaking into a bulk dimension, its waves would carry a subtle, telltale imprint, a slight deviation from Einstein's predictions that would be unmistakable. Meanwhile, astronomers will peer ever deeper into the cosmic microwave background, the afterglow of the Big Bang. The precise patterns in this ancient light could hold echoes of the pre-inflationary universe, potentially revealing the trans-Planckian physics governed by the geometry of the compactified dimensions. The confirmation of even a single one of these theories would trigger a scientific revolution as profound as the Copernican or Einsteinian shifts. It would prove that reality is vaster and stranger than our senses have ever allowed us to perceive. We would have to rewrite every physics textbook and fundamentally reconsider our place in the cosmos. We are not merely inhabitants of a universe, but beings living on a solitary membrane in a higher dimensional reality, our existence shaped by the invisible, coiled geometry of dimensions we may never directly see. The future promises to either validate our most ambitious dreams or force us to dream anew, forever changing the story we tell about the nature of existence itself. We have traveled from the tiny, curled-up loops of Kaluza-Klein to the vast, warped landscapes of brane worlds. We have seen reality reimagined as a cosmic hologram, its information painted on a distant surface, and watched as spacetime itself emerged from a web of quantum entanglement. These 30 visions are not established truths, but they are far more than science fiction. They are the bleeding edge of human curiosity, the sound of our collective mind straining at its limits, reaching for a unified understanding of existence. Each theory is a possible key to a lock we have not yet fully seen. They challenge our most basic assumptions about what is real, suggesting that the universe we perceive is a fragile shadow of a richer, deeper reality. This journey proves that the greatest human adventure is not outward into space, but inward into the nature of reality itself. So tell us, which of these ideas reshaped your universe? Which single theory left you staring into the night sky with a new sense of wonder? Let us know in the comments below, and subscribe to join us on our next voyage to the very edge of knowledge.